page 674, first half of section 9.7, probability. All right, in section 9.6, we were looking at all of the different ways that you could count things. Like we looked at combinations and permutations and fundamental counting order and different ways that I could count the total number of ways that something can happen. Our logic behind that is we're trying to prepare for probability. Because when I'm calculating the probability of something, probability is basically going to be the possibility of my event out of the total number of possibilities. So when I'm trying to find the total number of my possibilities, that's where those counting principles can come in handy. So on the top of page 674, it says any happening whose result is uncertain is called an experiment. So like when I flip a coin, the outcome of that event is uncertain. I don't know if it's going to come up heads or tails, so that's an experiment. The possible results of the experiment are outcomes. So at landing heads or at landing tails, those are outcomes of that experiment. And it says the set of all possible outcomes of the experiment is the sample space of the experiment. So if I went through and I said, what are all of the ways that this can take place? And I listed all of those out, in this case just heads and tails, then that would be my sample space. And any sub-collection of a sample space is an event. So if I chose one of those things and I said, you know, what's the chance that the outcome is going to end up where the coin flips and lands heads, then that would be an event. And so that's what we're doing with probability. We are calculating the possibility of the event out of the total number of possibilities. Sometimes it's helpful to actually think about what are all of the possibilities. And that's that idea of a sample space, when I literally give all of the possible outcomes of an experiment. So in example number 1, they asked me, find the sample space for each of the following. And the first one says one coin is tossed. So that's the example that we were just alluding to. If you toss a coin, it can land either heads or tails. So that's its sample space. That's the list of all of the possible outcomes. All right, look at B. B says, what if 2 coins are tossed? What if 2 coins are tossed? What can you get?
4.
Yeah, there are 4 different ones, right? And we want to list what those are, so give me some possibilities.
2 heads, 2 tails.
2 heads, 2 tails.
1 head, 3 tails.
1 head and 1 tail, but it could be in either order, right? So we could say 2 heads, 2 tails, 1 head and 1 tails, but in either order. It could be heads, tails, or tails, heads. All right, then for C, it says find the sample space if 3 coins are tossed. Now, we could sit here and we could just start calling stuff out, and we might end up missing 1 or 2 of them. So it's a good idea to kind of go about it in a methodical way. And maybe I start with what if they're all heads and move to what if none of them are heads, something like that. Okay, so I'm going to start with I flip 3 coins and all 3 of them are heads. All right, so then the next thing down is I flip 3 coins and exactly 2 of them are heads. If exactly 2 of them are heads, there's still several different ways I can write that, right? 2 heads and 1 tail can be written with the tail at the end, the tail in the middle, tail at the beginning. So we've looked at what if all 3 come up heads. We've looked at what if exactly 2 come up heads. What do you want to do next? If we follow that same progression.
All tails.
All right, we would want to check all tails, and then there's something else in between.
1 head.
Exactly 1 heads, right. So if there's exactly 1 heads, it could be at the beginning, it could be at the middle, or it could be at the end. And then, as you said, what if there are no heads at all, so that we have all tails? Now, I think I've gone about that in a methodical way. I think I've gotten all of them, but man, it'd be nice if there was a way to double check. Well, that's where fundamental counting principle can help me. Because I can go through and think of it as, okay, I flipped 3 coins. The first one can land how many ways? 2. The second one can land how many ways? The third one can land how many ways? So fundamental counting principle tells me I should have 8 in my sample space, and sure enough I do. So that gives me a way just to double check and make sure I got them all. So over on page 675, they say that if an event E has n of E equally likely outcomes, and its sample space S has n of S equally likely outcomes, then the probability of your event will be n of E over n of S. Again, it's just the possibility of your event over the total number of everything that's possible, total number of possibilities. Now, they mention there in that definition equally likely outcomes. If I flip a coin 50 times, it's not likely that it's going to land 25 heads and 25 tails exactly, because this is the real world. So, you know, in a perfect world, everything would be equally likely, and that's what we're going to assume for these problems, because there's no other way to do these if I don't know that I can depend on them, you know, a die landing 1, 2, 3, 4, 5, 6, it being equally likely. A coin flipping and it landing heads or tails being equally likely. Pulling a card from a deck of cards and all of them having the same chance of being pulled. So I do need to assume that for our experiments, even though in the real world that wouldn't necessarily be the case. There on page 675, they give me a couple of more bold print terms. Impossible event and certain event. When we calculate a probability, it's going to be a number in between 0 and 1. If the probability is 1, it's a certain event. If the probability is 0, it's an impossible event. Okay, so let's say it's raining outside right now, and we say, what's the probability of it not raining today? Well, that's impossible because it's raining right now. That probability is 0. Whereas if we said, what's the probability of it raining today, and I look outside and it's raining right now, that's a certain event. It's happening right now. You might think of that as like 100% chance of rain. You can think of it that way. We just write our probability, instead of writing it as a percent, we write it as a decimal. So if you took 100% and you wrote that as a decimal, it would be 1. So that'd be a way that you could think of that. So probability is going to be a fraction or a decimal in between 0 and 1, but it can be equal to 0 and 1. 0, an impossible event. 1, a certain event. All right, look at example 2. For example number 2, it says 2 coins are tossed. What's the probability that both land heads up? All right, so if 2 coins are tossed, because we've already done the sample space up here, we know that we have 4 total possibilities. If I hadn't drawn that sample space out, I could do fundamental counting principle or just kind of think it out in my head to get my total number of possibilities for my denominator. Out of those 4, how many of them were both heads up? Just one of them, right. So the probability of my probability is going to be the possibility of the event. There was only one way that could happen. Out of the total number of possibilities, there were 4 different outcomes possible. All right, look at B. B says a card is drawn from a standard deck of playing cards. What's the probability that it's an ace? Okay, I'm not assuming that you know the makeup of a deck of cards, so I've listed it here on the board for you, and that will stay up during tests, during quizzes, everything else. So if you need to jot that down so that you have it for homework or something like that, feel free to. But in a standard deck of 52 cards, there are 26 red and 26 black, so half and half. In those 26 red cards, there are 2 suits of 13. There's a suit of 13 hearts, and there's a suit of 13 diamonds. In the 26 black cards, there are also 2 suits. There's a suit of 13 clubs and a suit of 13 spades. And each of those sets of 13 are made up of the exact same thing. They're made up of a 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, king, queen, and ace. The jack, king, and queen are also referred to as face cards because they're the only cards that actually have a face on them. An ace is not considered a face card because it doesn't have a face on it. Okay? So those will be the things that they'll ask you about. They'll ask you about the probability of picking a particular color like red or black, or the probability of picking a particular suit like hearts, or the probability of picking a particular card like an ace, or like the face cards, that group of 3. Okay. So for B, it had said a card is drawn from a standard deck of playing cards. What's the probability that it's an ace? So how many cards do I have to choose from? 52 in the deck, right? And out of them, how many are aces? 4. So my probability would be 4 out of 52. Now we always want to give our probability in lowest terms. So I would simplify that fraction down to 1/13. All right, look at example 3. Example 3 says 2 6-sided dice are tossed, so that's just a normal pair of dice. What's the probability that the total of the 2 dice is 7? All right, so first off, I need to figure out my denominator. I need to figure out the total number of possibilities. So I could sit here and write out a sample space. I could do 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 2, 1, 2, 2. It's going to take a while, right? Better way of doing that we learned in section 9.6 is to use fundamental counting principle. The first one can land how many ways? The second one can land how many ways? So if I multiply those, I have 36 possibilities in my sample space, right? Then I need to go back and figure out how many different ways I can get the sum that they've asked for, which in this case is 7. So again, I want to go about this in a methodical way so I don't miss any of them. So maybe I start with 1 and say 1 and what? 2 and, 3 and, 4 and then 5 and, 6 and so we've got our possibilities. Now the reason that we count, for instance, 3 and 4 and 4 and 3 as 2 separate rolls, you can think of it as like, what if one die was red and one die was green? A green 3, red 4 is not the same thing as a red 3, green 4, right? So I need to be sure, maybe the 3's on the green die or maybe the 3's on the red die. That makes a difference then in the roll. But if I had something like 6 and 6, and of course that would be a different sum than what we have here, but if I had something like 6 and 6, red 6, green 6 is still green 6, red 6. I don't count that as 2 separate rolls. Okay. So we had 1, 2, 3, 4, 5, 6 different ways that we could get our event, a sum of 7. So we could say that's 6 over 36. And again, we're going to give that probability in lowest terms. So we would simplify that down to 1/6. All right, look at example 5. Example 5 says in a state lottery, a player chooses 6 different numbers from 1 to 40. If these 6 numbers match the 6 numbers drawn by the lottery commission, the player wins or shares the top prize. So what's the probability of winning the top prize? Now, something that you may not know is that with the lottery, it's any 6 numbers. They don't have to be in order. So that's a combination. So if we're talking about how many different ways can I choose those numbers, I want to go back to section 9.6 to my combination formula, NCR. So for N, how many numbers do I have to choose from? It says that I'm choosing 6 different numbers from 1 to 40. So how many do I have to choose from? 40. And how many am I choosing? 6. So I'm going to do that combination, 40C6. I can work it out by hand using the formula, or I can throw it into my calculator, depending on what setting I'm in. And you can see there's almost 4 million different combinations of those 6 numbers. Out of those, how many are the correct combination? 1. So I have a 1 in almost 4 million chance of winning. So I have never bought a lottery ticket in my life for 2 reasons. Number 1, I'm a mathematician, and looking at that is just a total waste of my money. Those kinds of odds are just crazy. I would be throwing my money away. Number 2, as a Christian, everything that I have came from God, and it's entrusted to me, and I'm supposed to be a good steward of what He's given me. So I have a really hard time justifying, okay, I'm going to take $10 and play these kinds of odds, or I'm going to take $10 and give them to a missionary in Africa that's feeding the starving, right? So if I'm going to be a good steward of what God has entrusted to me, that comes into my view of the lottery as well. So, all right, look at example 6. Example 6 says the number of colleges and universities in various regions of the United States are shown in the figure here on the bottom page 677. One institution is selected at random, so what's the probability that the institution is one of the two north central regions? All right, so for my denominator, I have to find the total number of possibilities. So I'm going to have to look at that graph that they gave me and find the total number of colleges and universities. So I started with South Atlantic, the little purple piece over there that was 607, and I just went counterclockwise. So I did South Atlantic 607 plus Mid-Atlantic 598 plus New England 257 plus East North Central 578 and so on the rest of the way around, so that we could get the total number of colleges and universities for our total number of possibilities. All right, then for my numerator, for the event that I'm trying to calculate the possibility of, it says, what's the probability that the institution is in one of the two north central regions? So if you look at the top of that map and you kind of look in the center, you'll see west north central and east north central. That's what they're referring to there when they say, what's the chance that it's one of those two north central regions? So if you'll notice, West North Central has 397 and East North Central has 578. So that's where I'm getting those two values for my numerator. Okay? So if I combine those, I get my probability is 975 over 3,696. I may be here for 5 minutes reducing that, right? Did you know your calculator will reduce fractions for you? If you throw that into your calculator, 975 divided by 3,696, it's going to change it to a decimal. If you will then ask your calculator to change that decimal back to a fraction, so that's your math button, where you go to math and you ask it to change your decimal back to a fraction, or it's also under the alpha F1 if you have the new operating system. There's an option there of changing a decimal to a fraction. It will change it back to a fraction for you, but when it does, it will give you the fraction in lowest terms. So like you could try it even with something more simple on your calculator where you put in like 5/10 and hit enter and it'll tell you 0.5, and then ask it to switch that back to a fraction, it'll switch it to 1/2. It won't switch it back to 5/10. So that's an easy way to get your calculator to reduce for you. Because, I don't think we would have any trouble reducing it down to the 325 over 1232, but I would probably be sitting here for a little while longer thinking surely that has to reduce and trying every number on the face of the earth to make it reduce, only to find out that it's in its lowest terms already. All right, so here is our homework on page 682. We're doing 1 through 19 odd, 33, challenge 39.